Lecture 16, part 2. So in the previous part, we talked about uniform cost search. And in this one, we're going to continue and change the priority queue to based on the heuristic instead of based on the current cost, as in uniform cost search. So the heuristic, as a reminder, is just an approximation of the actual cost from the current state to the goal state, which is denoted by H star. So here it's just approximation, so it may be incorrect. That'll be why the best first greedy search may not be a great idea. But what we're going to do is we're going to try this first and then talk about the A search, which is the better variation of this. So let's use the maze example again, the same one. And let's see, this one here. And okay, so let's start from 1. We need some kind of heuristic. So let's put it here. Priority queue. Let's start with 1 in the middle. And a heuristic H of S. So in P4, you are going to use the heuristic as the distance, the approximate distance from each point, from each state to the goal state is the Euclidean distance to the goal state. So for example, if you are here, then the heuristic is going to be the Euclidean distance, which is square root 2. And the actual distance is like this, so it's longer, but it's kind of a good approximation. So if you are, say, here, it's kind of closer. If you are here, it's exactly the same. So for most of these, it's not a great approximation, but it's good. However, the Euclidean distance is too hard to compute, so let's just use the Manhattan distance. Actually, you need to implement the Manhattan distance version for P4. I mean, actually, it's P5. Sorry. So in P5, and I will use the Manhattan distance, which is using 2 here to approximate the distance from this state to the goal state. So let's do that for state number 1, so Manhattan distance. So starting from here to the goal is 1, 2, 3, 4, 5. So that's our Manhattan distance. And now let's still expand the thing, expand the front of the priority queue, and in queue the successors. So the successors, there are 2 of them, 2 and 3. Let's see, what is 2? 2 seems to be further from the goal, and 3 seems to be a little closer. So let's do it this way. Let's actually put 3 here. So the distance from 3 to the goal is 1, 2, 3, 4. Let's use another color. 1, 2, 3, 4. So this is 4. The distance from 2 is just 1 plus the distance from 1, so it's 5. Again, they're Manhattan distance because we don't want to compute these Euclidean distance, but you can. It's just like 4 square plus 2 square root. But in any case, we're going to prioritize 3. Now you see why this kind of algorithm is good, because we're not going to expand 2 first. We're going to prioritize the one that's closer to the goal, which is 3 here. Let's get rid of 3, and let's put 4 here. And 4 is actually even closer. It's 3 units away from the goal. And now let's dequeue4, and in queue 5. 5, it seems it's further. So 5 is again 4 units away from the goal. So this is our 5. And 6, unfortunately 6 is even further, so 6 is here. But again, we are never expanding the 2 here, so that's good. And by the way, I wrote this incorrectly. This should be 6, right? So it's 1 unit further from 1. So far, all of these are closer to the goal, so we never need to expand 4. So after 6, we expand 6, and then we get 7. 7 is going back to 4, so somewhere in between. Let's put it here. And then 7 goes back to 8. And now we're getting closer and closer, so we just expand and get 9, 10, and 11, and so on. So that's the idea here. It seems it's working. I think the reason it's working is because we have some kind of reasonable heuristic. However, if we don't, then it does not work. So let's use the other example that we use for uniform cost search to show that. And let's see this one here. And I will write down the priority queue here, and we need the H. So now we're given the heuristic, and here the heuristic is actually equal to the actual minimal cost. Right? So A is 3 units away from G, so that number is actually correct. In any case, let's start with an A in the middle, and the heuristic is 3. Let's include B and C. So C has a lower heuristic, so C from A and B from A. This is 1, this is 2. So now it's immediately problematic because we don't really care about how we get to C. We only care about the heuristic of C. So that's why C from A, not C from B, C from A is actually closer. So that does not make any sense. But, well, we'll DQ this one, and then we'll include G, and that'll be 0. So again, as a reminder, we always need to DQ G to finish. We cannot just stop here. So we'll DQ G, and then when G is DQ, then it's okay. Because the reason is sometimes we'll put G like later, so we need to expand the other ones first. So we will have examples like this in the Canvas lecture. But here, the example we put G just at the beginning, so it's not a problem. So we can just directly DQ it. So now G came from C, C came from A, so the actual cost is 1,000 if you use this best first search, so it's not working actually. So it does not pick up the path of G from C, C from B, and then B from A. So that's a counterexample of the best first or greedy search. And that's another summary of how to implement it. You actually don't need to implement it for P5. And it turns out the greedy search is incomplete because of some cycle problem. So it can go in cycles and never stop. And it's also not optimal. Obviously, we have an example already. So next, we're going to upgrade it again to the one that we are actually going to use. Unfortunately, the name is really bad. It's a search is not a search, it's a search. And sometimes people say that it stands for always be optimistic. I'm actually not sure the person who invented this is calling it A because it's always be optimistic, but it's, well, just a search. In any case, we're going to prioritize the states with the lowest G plus H. So we consider the cost so far, and we also consider the costs that we estimate in the future. So basically, this is kind of an estimate of the total cost. So we're going to expand the states with the lowest estimate of total cost, and we want to start there, and then hopefully we'll search only the important ones. Okay, so we're not going to go through the maze example, and we are going to go through the one that's wrong with best first search. And let's look at this. Okay, so now the table needs to be larger. There seems to be something wrong with the slide. In any case, priority queue and G and H and G plus H. So we need all of these information, and we start from, say, A. Let's put A here. G so far is 0, nothing happened yet. The H is 3 because we know from the number the sum will be 3. Then we DQ this and include the successors. So the successors are B and C, both from A, and which one is larger? So B is actually better, so let's put B from A here, and it's the G, the cost is the cost of A plus the distance from B to A, which is 1, and H here is 2, and the sum is 3. So they're actually the same. I'll just put it in front. And the other one must be larger. So C from A is the cost of A plus the cost between C and A, which is 999, and the heuristic is 1, so the total cost is 1000. So now we're never going to do that. And next, we're going to get rid of B and include the successor of B. There's only 1 from C to A. C to B, and it's the cost of B, which is 1, plus the cost between B and C, which is 1, so 2, plus the heuristic, which is another 1, so it's another 3. So I can put it in front or at the back, is the same. So the last one is we're going to dequeue this. So now the one we dequeued is C from B, not C from A. So that's appropriate. And G from C. And we have the cost is copy this cost 2 plus the distance between the two, which is 1. And then the heuristic is 0, so it's 3. Okay, as I said, we need to get rid of that. And then we're done. So when we pop or when we dequeue G, then we're done. So it seems here we get G from C, C from B, B from A, and that indeed is the shortest path, and that G plus H is correct. Okay, so let's do one more example because it's kind of an important algorithm. And let's see. Okay, so our priority queue and our G, H, and G plus H. Let's start with A in the middle again. G is 0, H is 2, so the total is 2. Let's dequeue A and include B and C. So B is better, B from A is better, and B from C is kind of the same. So B from A is G is 1 and H is 0, because here somehow it's wrong and it's 0. So this is 1. And B from C, let's see, G is, that's actually not right. I'm sorry about this. This is C from A. So C from A is, the G is also 1 and H is 1, so the sum is 2. Okay, so now we're going to dequeue B. When we dequeue B, we get G. G is somewhere here. And the cost is, whatever the cost is originally from B, and we're going to add the cost between B and G, which is 999, and we plus H is 0, so it's 1000. So we put it at the end. So now I guess you can see why we need to not stop here, because we have G, but we didn't pop G, because this is obviously not the best one. So next one, we're going to pop C first, so we're actually not going to pop this G. So let's do that. Pop C from A, and then we add G. Where is G? G can be either in between, or let's just put it here. G from C, and the total cost so far is 1 plus the distance between C and G, so it's 1. And next, the heuristic is 0, so it's 2. So now we can pop this G, and then we are done. So here G is at the front, and it's G from C and C from A. So now we get the right path, which is that one. Okay, so that's another example showing why we need to pop G at the end so that we actually get the smallest one. So the moment we put in G is not the moment we stop, basically. So let's talk about yet another example. Let's see, the priority queue and G, H, and G plus H. And it seems everything at the beginning are the same, but let's repeat it anyways. So start from 0, H is 1. That looks wrong. And then we can go to B. B is a bit larger, so B from A. And C from A is even larger, so let's see. B from A is 1 plus 1 is 2. C from A is 1 plus 900, and it's 901. So next we're going to get rid of B. So we need to get to D. So it's somewhere in between. So I apologize, I should probably move it to the front. The next one we're going to add is D from B, and the cost is whatever the cost of B is plus the distance between B and D, so 1 plus 2, and the heuristic here is 1, which is kind of wrong, and the total will be 4. Okay, still not great. Get rid of this, and then we add the successors, and the successor now is G, and G is not put here because the cost to G from D is we need whatever this number is 3 plus 999, this cost between D and G. Again, whatever the cost is from D, and we add the cost between D and G. So the H is 0, so it's 1002. So again, it's another example why we shouldn't stop here. This is obviously not the right way. And next, we're actually going to pop C. So we wasted so much time on the B pass, which is not right. And let's pop C. And when C is popped, then we get D from C. So now another problem that we see is we get multiple of these to the same pass, and we actually update them. So we actually get the best one. So G is 1 plus 1. It's actually smaller than that one. So let me actually draw it correctly. DC is G is 1 plus 1, and H is 1, and then the total is 3. Okay, so let's get rid of this one. And at the end, we have G from D again. Well, these two are both G from D, but they have different costs, so we need to have two different separate entries in the queue. And the G value here is whatever the D value is from that one. This comes from the G from D from C one, and let's see. So this 2 plus 999, and then we have 0 here, and then it's 1001. So now we can dequeue this, and then we're done. Okay, so as I said, I will do more examples, and these are the only 3 I want to show you about repeated states, and also we need to pop G at the end in order to figure out the best path, and hopefully it gives you some intuition of why A would work. Unfortunately, A is still not optimal, and we will talk about this in the next part of the lecture, but this again is a summary of how you implement A, and the performance is that A is complete. A is not optimal. The reason is because we can have incorrect H values. So we need to restrict some value for H, so some admissible heuristic in order to make A optimal, and that's called the A star search, and we will talk about this in the next part.